This is another taping of Climate Matters TV. I'm your host, Stuart Scott. It's a TV program coming to you live from the COP22, Conference of Parties, the Kyoto Protocols. We're here in Marrakesh, Morocco. Here's my email address so people can contact me. And today's guests, Dr. Hugh Hunt, the Department of Engineering at Cambridge University, and Dr. Peter Wadhams, Emeritus Professor of Ocean Physics, also from Cambridge. And the title of this show, Can Technology Save Us? Or it can be rephrased, Can Engineering Save Us? So that you don't think that this kind of technology is going to save us. Now, we'll start off with a fairly complex diagram, but we'll just look at a few pieces of it. This is the pros and cons, or the what recommends and what runs counter to using geoengineering, or more specifically, the supply of negative emissions technologies. Let's look a little closer at the diagram. There's the socio-political acceptability. That is, are people going to be protesting, marching in the streets just because of the word? Biophysical climate impacts, which need to be very well researched to make sure that it's benign technologies as far as we are able to. Gentlemen, just jump right on in if I come to a point that is hot topic for you. The land area required. We have competing needs now, needs for a large and expanding population and needs for growing biomass. There are competing land needs. Those have to be analyzed. And of course, the costs, since costs are so dominant in human civilization. If it doesn't pencil out on the bottom line, then people are not going to want to do it, or not be inclined to do it, unless they have to, such as in World War II, when we had to spend the money because we could see the enemy. This is an insidious enemy. I like to say the enemy is us. And then early testing and scaling. All of these things have to be, they're complex, but we have to start now. I think my guests will agree. Now, I'd like to ask Hugh to comment on this article from New Scientist.
Well, the SPICE project, Stratospheric Particle Injection for Climate Engineering, was a UK-funded project. It started in about 2010 and it ran for about 5 years. And part of the project involved doing an experiment. The experiment was to build a small balloon at a height of 1 kilometre, which is 3,000 feet, and to spray water, about a bathtub full of water, up a pipe. And in fact, this is the very pipe that we had planned to use.
Was that actually a sample of the pipe that you were going to use?
This is the pipe that we had planned to use. Mm-hmm. Well, we never did the experiment because it was deemed to be controversial. If you want to know what controversial means, well, I was in charge of this project. Nobody phoned me up. Nobody was standing outside my building with placards. Nobody sent me any emails. No reporters, no newspaper reporters talked to me about it. Nobody threatened my family. Nobody did. I had no idea that it was controversial until it appeared in these magazines and journals. One of the things you might be able to read at the bottom is that at issue was a patent on the technology. Well, it turned out really that there was no issue. One of the things about it was that if there's a patent, then surely that means that somebody is in it to make money out of this, and we don't want anybody making money out of any of these technologies. But the reason why you might want to patent things is because in order to develop a technology, you need to have something that you can say, oh, this is my idea and I want someone to help me develop it. But you've got to start small. So now the very small experiment that we plan to do involved a balloon, a blimp about this sort of size, and people thought this was fine, actually, if you talk to people about it. But the objection was that this was the beginning of the slippery slope into geoengineering. Now, if you look at that balloon, does it look like a slippery slope into geoengineering? Well, it's really important that we get the framing right and that we talk to people. Well, we did talk to people. One of the things we went to great lengths of within the SPICE project was to have public engagement exercises. We got several groups, each group about 12 people over 2 days. We talked about generally the climate and about urgency and about geoengineering. And then we asked people, well, what do you think? Is this a dangerous technology? And on the whole, they were cautious, but they were thinking, thank heavens somebody is doing some research into fixing the climate problem. So generally, the technology was well received, but the media didn't present it that way. And now, as a result of fairly adverse coverage, we were not allowed to do our experiment. Now, if we're not allowed to do experiments, then how are we ever going to develop a technology to a point where, if one day it turns out to be necessary, we might need to use it. Now, I'm not pro-geoengineering at all, but I'm pro-research. I'm hoping that geoengineering will never be needed, but I worry about the melting of the Arctic. And if the Arctic does disappear, well, I think we're in big trouble.
Yes, it's a parallel here with oil spills in ice. This is potentially a very bad thing, but for 40 years there's been no research possible because you're not allowed to do experimental oil spills. But this question about disappearance of ice, there's a technology called marine cloud brightening, in which you inject through tall masts on ships very finely divided water particles into the bottom parts of stratus clouds, and each particle as it evaporates leaves a salt crystal behind, and this brightens up the cloud. It makes it whiter, so it reflects more radiation, and that's been calculated that it could put a sticking plaster on global warming, just like the release of particles into the stratosphere. But the question arises just in the same way: how do you test this without arousing public disquiet? And in the case of marine cloud brightening, firstly, you can do it by using a single release point and time coding the release of your particles, and then looking for a response in the cloud as to how whether you can detect the signal of the cloud brightening or not brightening under the effect of a single release point. But if you use a number of them, it's not the several hundred that will be needed on a full scale, but perhaps a few dozen or a dozen, you can place them in certain positions where, at least according to theory, they will have a maximum regional effect in one particular part of the world. And the modelling of maximum Arctic regional effects involves putting a lot of clouds in the subarctic, a lot of bright clouds in, and this is the model shows that if you do that and do it on a smaller scale, you ought to be able to get a detectable increase in the amount of sea ice. So the result would be the light green line would be the ice edge, where at the moment the red line is the ice edge. So here's ways in which you could try this out, not on the planetary scale, but on a scale where you can, if you can detect the response that you hope for, then it's been a positive trial. And the hope would be that because you're releasing water into a cloud, that this won't arouse some of this ill-advised disquiet that you get with geoengineering, because water vapor is a pretty benign substance.
So we're not talking about salt water now, we're talking about fresh water.
Yeah, it's salt water that's used.
Okay. Okay, but it is, as you say, fairly benign to be spraying seawater, salt water up into the clouds and having it fall down.
Mm-hmm. But I think one of the things that is really important when we're talking about the engineering solutions is thinking about the timescales and the cost. This slide here shows the cost of delivering about 10 million tonnes per year of sulfur dioxide into the stratosphere. Now, 10 million tonnes a year sounds a lot, but it's tiny compared with the 35 or 40 billion tonnes a year of CO2 that we're putting into the atmosphere. So it's less than 0.1% of the CO2 emissions that we're producing.
We're talking about millions of tonnes here, but what's required is the withdrawal of billions of tonnes.
Yeah, so if we wanted to withdraw CO2 from the atmosphere, we're talking about tens of billions of tonnes. If we want to do solar radiation management, which is a method of cooling the planet by putting reflective particles high up in the stratosphere. Well, the eruption of Mount Pinatubo in 1992 demonstrated that we could put about 10 million tonnes of sulfur dioxide into the stratosphere to get a cooling effect of the order of 1 degree. Now, this graph here shows an estimate of the costs on the vertical scale on the left-hand side. But if you think about it, the cost of building a nuclear power station is the order of, say, $10 billion. So these costs are not actually that great. Now, I was looking at using tethered balloons as a technology to put geoengineering materials, say sulfur dioxide, up into the stratosphere, because if it can be made to work, it would be pretty cheap. Now, maybe cost doesn't matter too much, but if it's cheap, then you can pretty well expect politicians will say, oh, it's cheap, let's do it. So the real worry is if something's cheap, then we'll probably launch into doing it without thinking of the consequences. And that is why the research needs to be done, because we want to make sure that if it turns out to be a really bad thing to do, we know about it. And actually, my feeling is that it would be a really bad thing to do, but we don't find that out until we do the research. The other thing on this graph is the timescale for development. We need things that can be done quickly, because the clock is ticking. We're running out of time to deal with a warming climate. Now, the kinds of things that we could do quickly, we could use aircraft. The most obvious technique for delivering aerosols into the stratosphere is with aircraft. And actually, we could probably start doing that this year if we wanted to do it. So the technology isn't far away at all, but the understanding of the consequences that's what's lacking.
I was going to interject that I think one of the bad raps that proponents of or researchers in geoengineering get is that they're deemed to be reckless. They have children too. I think that's an unfair mudslinging, but they have to be allowed, as you said, to research and find the promising technologies and figure out how to bring them to scale.
Yes, because in a way the most reckless thing is simply to be putting greenhouse gases into the atmosphere at such an enormous rate that it overwhelms the kind of natural levels that the Earth can manage.
But we've been doing that for so long that we don't think of it as reckless. It's part of the paradigm. It's the business as usual. I'd like to return to the idea of money, how money plays in all this. The aspect of it needing to be financially profitable or judged to be worthwhile in a world that estimates everything only in terms of money.
Well, I could just mention one case I heard of. That I was a company that contacted me just after my book came out saying, oh, we've got a method for direct air capture of carbon dioxide from the atmosphere. People have been looking at these direct methods for some time of passing, as Hugh has said, passing air over a system for absorbing the CO2. And this one method is a kind of artificial trees with absorbent materials. Now, this company says they've come up with a method that could do this job at a very low price, or a price of less than $40 a tonne, which is a target price that you're trying to get to that will be acceptable. But they say, well, we're doing it for as a business, producing carbon nanotubes and producing materials. So since, although the person who developed this method is at a university, Columbia University, all the work is being done by a company. So in terms of profit, you'd have to find government funding that would persuade the company to, in this sense, stop being a company and start being a public service for the planet as a whole, if the technique actually works.
So we're a little bit shackled by the profit motive there.
Yes.
Mm-hmm.
I think that we have to think about what is the cost of removing CO2 from the atmosphere. And I think that if we're looking at removing 10 billion tonnes of CO2 from the atmosphere, which is a a quantity of material which is larger than any other materials handling exercise that we have ever done. We do not handle 10 billion tonnes of coal. We don't handle 10 billion tonnes a year of steel or of oil. In fact, the combined handling of oil, coal and steel is of the order of 10 billion tonnes a year. So if we are going to start up an industry to handle and sequester 10 billion tonnes of CO2 per year, well, I think we can reasonably expect it to cost about the same as it costs to handle steel, coal and oil. And that is not just $10 billion a year, not 100 billion, not 1,000 billion. It's trillions of dollars a year, which we can't ignore. So we've got to deal with the actual tangible costs. And if we can't expect to be spending tens or hundreds of trillions of dollars a year, big numbers, on getting rid of CO2 from the atmosphere, well, I fear that we're not going to meet the Paris 2-degree target. We're not going to meet a 3 or a 4-degree target. And once we start failing to meet 3 or 4 or 5-degree targets, then I fear for the future of the Arctic.
Yep. Yes, I think that's true. It's the scaling factor, as Hugh says, that's the vital one, the scaling factor in cost as well as the scaling factor in technical feasibility. So we really have to take that very, very seriously and not be so kind of mindlessly or endlessly optimistic. We hope that we can be endlessly optimistic, but we have to realise at some point this is going to run into the problem of is the world prepared to commit such a large fraction of its resources to the question of saving itself from climate change. And of course it should, but that will be something where it will need persuading that this is the case.
I think we have a cognitive issue here as well in terms of the structure of the human psyche, where if you're asking, let me start at a small scale, if you put a whole bunch of refrigerators in a row and you have energy usage tags on each one, and this one will only use $100 or 100 pounds a year worth of electricity, and that one will use $500 a year worth of electricity, but that one is $100 cheaper, then people will buy the one that's $100 cheaper. We're not good structurally in our cognitive abilities at comparing the amount we have to spend now with the amount we'll save. And if we scale that up, I know Lord Stern, Nicholas Stern, who's fairly famous in the climate world for having analyzed the economic impacts of not doing anything, of avoiding dealing with the climate. Peter, I think you're more up on his recent work than I am. Can you comment about that?
Yes. The economic model he was using estimated the total cost to the planet of climate change, and it was coming to very large numbers, of course. But he's now saying these were underestimates. And one case where the Stern model was used on a smaller scale was to look at what would happen if we did have this methane outbreak from the Arctic. And some colleagues and myself did an analysis using Stern's model, and it turned out that if you have a methane outbreak, then the total cost of that to the world in terms of climate change would be $60 trillion. Now, that's a huge sum, and it means that the cost of avoiding a methane outbreak, that using these techniques to cool the planet or bring back sea ice in some way so that you don't get methane being released, or drilling under the sediments to tap the methane off. All these are very, very expensive techniques. The people might say, and politicians do say, well, we can't afford to spend. In fact, a typical politician statement is, we can't afford to spend these things on these green issues. That's a sort of British politicians type statement. But the reality is, if you don't, you have $60 trillion of expense coming along the road because of the methane outbreak. So that's
That's why, Peter, the worry we all have about geoengineering, spraying stuff up in the stratosphere, it's going to be so cheap. So politicians are not going to be willing to spend the money on things they ought to be spending the money on. And then if you think about why is it that we put so much CO2 into the atmosphere, well, the answer really is because it's so lovely. We can heat our homes, we can fly to lovely places, we can drive to exciting adventures. There are so many things that we love doing for generating CO2, and we will pay whatever it costs to generate CO2. When will we be willing to pay whatever it costs to get the CO2 out again? This might seem a bit irreverent, but we're in this small swimming pool and we're all pissing into this pool, okay? And at some stage or other, we've got to figure out how we clean up the mess. And firstly, we've got to stop pissing. And secondly, we've got to figure out what to do with all the piss that's already there. I'm afraid it's as bad as that. We've got to do something about it.
At least we're not pooping in the pool.
At least we're not, well, maybe not yet.
Arguable. We have just a few minutes left, and we'll take a couple of questions from the audience if we have any.
My name is Tatiana Pichugina. I'm from online media Scientific Russia. My question is, couldn't you find a rich guy to support your projects? Some investors, private investors, I mean.
Like Richard Branson, rich private investors, that sort of thing?
We can get private investors interested in geoengineering. My worry is that the obvious private investor who might be interested in geoengineering are the oil companies. Now, if the oil companies are interested in geoengineering, it kind of makes us think that they're interested in geoengineering so that they can carry on burning oil. But maybe that's unfair. Maybe oil companies are beginning to realise that there's not money to be made out of burning oil anymore. So maybe they'll soon realise that governments are going to pay good money for geoengineering. So it could be that, as sad as it may sound, the very technologists that got us into this mess are going to be the ones we're going to ask to get us out again too.
And it could be speeded up by the fact that renewable energies, there's many types of renewable energy that are now becoming cheaper than oil. For instance, solar photovoltaic is dropping in price all the time. So there will be a world not far ahead where solar energy becomes a base load energy source, and the oil industry will feel oppressed. They'll be asking for special subsidies, because they get them already, but special subsidies to remain in business providing oil when there's so little demand for it. So that may cause them to feel they'd like to help pay for getting rid of CO2, because the changed world means that they're no longer making huge profits.
But I think the question perhaps was looking for maybe Richard Bransons of this world, Elon Musk's of this world to get interested. Well, if you've got any good contact with them, then let us know.
Okay, I think we're about out of time, so I want to thank you all for coming. Again, as I promised, there's my email address if you'd like to get in touch, and I can forward questions to our two guests, Dr. Peter Wadhams and Dr. Hugh Hunt, both from Cambridge. Thank you very much for coming. Please watch some of our other shows at Climate Matters TV. Thank you.